Greetings, Physics 182 students. In this example, this is Professor Jeff Wilkerson at Luther College. For those of you who aren't Physics 182 students, if you happen to be watching this, in this example, we're going to calculate the amount of energy it takes to turn a block of ice from negative 20 degrees Celsius into steam at 200 degrees Celsius, ignoring some of the complications that come along the way. So we're going to break it down, an easy 5-step process, as we'll be talking about in class. Probably will have talked about in class already by the time you see this. So we got a 5-step process here. First we heat the ice, then we melt the ice, then we heat the water, then we boil the water, then we heat the steam. Okay? 1, 2, 3, 4, 5. Yep, got them all right there. So we're at this 5-step process to get ice into steam. So the first thing we do is we start with the ice and say that the heat required to raise the temperature of the ice up to the melting point is mc delta T. Let's do 2 kilograms of ice, negative 20 degrees C to steam at 200 degrees C. Okay, so that's going to be, it takes us 20 degrees to get up to the freezing melting point for ice, water. So that's going to be 2.0 kilograms. Let's add a decimal point there for the heck of it. We need the specific heat of ice, not water. So the specific heat of ice, where I looked it up, you might find different numbers in different places, but where I looked it up, it was this, 2.22 times 10 to the 3 joules per kilogram per Kelvin. A degree, remember it's a delta T here, so a degree Celsius is the same as a Kelvin step, so that's going to work out just fine for us. We don't have to do a conversion right there. There's the 20 Kelvin step that we do, and we get that that's 8.88 times 10 to the 4th joules. Okay, so we've now got our block of ice at the correct temperature. Try to melt it. Let's melt it. How much heat is it going to take to melt it? Well, it's going to be Q is equal to the mass times the latent heat of fusion. Okay, that's, remember now what we're doing is all the energy is going into separating those molecules, to pulling those molecules apart just a little bit, so that they're not locked in some sort of lattice now. They're free to move. Remember, we're going to a fluid state. It's a deformable substance that's free to move. And so increasing that separation a little bit, and I have that mass is 2.0 kilograms again, and the latent heat of fusion that I looked up here was 3.33 times 10 to the 5 joules per kilogram. No per Kelvin this time because we're not raising the temperature. We're just keeping the temperature locked at 0, and that ends up being 6.67 times 10 to the 5th joules. It took us almost 10 times as much energy to melt that ice as it did to raise it to 20 degrees to get it to the melting freezing line. Next, we got to heat the water. So we go back to something that looks like this. It looks like Q is equal to mc delta T. We got to go from 0 degrees Celsius to 100 degrees Celsius. So delta T is going to be 100 this time. Mass is still 2 kilograms. C is different because now it's C of liquid water, not C of solid water. So what I have there is 2.0 kilograms. Where I looked that up, 4.189 times 10 to the 3 joules per kilogram Kelvin. It's back to a per Kelvin in here now because we got a delta T. And remember that delta T is 100 Kelvin. And that, when I plugged it in, looks like it was 8.38 times 10 to the 5th joules. Okay, so same order as the fusion, but we had to raise it 100 degrees here this time. Now we gotta vaporize the water. We gotta boil the water away. Again, fixed temperature while we're undergoing a phase change. So we have that fixed temperature, and all of our water's going in to now really separating those molecules. In the gaseous state, those molecules don't know the other molecules are there by and large. It looks like an ideal gas, and so there's very little intermolecular interaction that goes on right there. So we're basically breaking all of that intermolecular attraction right here. And we go back to Q is equal to mL sub V, the latent heat of vaporization. And it's going to be 2 kilograms again. And the latent heat of vaporization looks like 2.26, where I looked it up anyway, times 10 to the 6th joules per kilogram. Again, no per Kelvin, because we're keeping the temperature locked at 100 degrees Celsius as we're doing this. This is almost an order of magnitude larger than this, latent heat of vaporization. This is a general rule that you'll find, is that to really separate those molecules, to really do this break, it takes a lot of energy. So the latent heat of vaporization is significant relative to the latent heat of fusion. And so we've got that going on here. We can stick those numbers in, and we end up with, it looks like, I can't read my writing, 4.512, maybe 4.512 times 10 to the 6th joules is the total amount of energy. So that's the biggest energy step of all of these things that we've done so far, because of that latent heat of vaporization. That's a hard transition to make. So 5, now we got to heat the steam. We're going to heat the steam another 100 degrees, like we heated the water 100 degrees. So we go back to Q equals mc delta T. And now it's still 2 kilograms. Delta T is 100, but now it's the specific heat of steam, of gaseous water, not liquid or solid water, and that's 1.96 times 10 to the 3 joules per kilogram Kelvin times 100 Kelvin. Looks to me like it's going to be 3.92 times 10 to the 5 joules. If we want to know the total energy, which we do, Q total is just Q1 plus Q2 plus Q3 plus Q4 plus Q5 is equal to, I'm sure I added that up someplace. I got 6.50 times 10 to the 6th. 6.50 times 10 to the 6th joules. 6.5 megajoules. Of that, almost 2/3 of it, of that, almost 3/4 of it right here was the vaporization, the boiling of the water. So that's a significant step that we had in here. So there's your process to turn, figuring out how you want to calculate the energy it takes to turn ice into steam at different temperatures there. Okay, so that's our sample problem for a little bit of calorimetry, a little bit of heat changing phases of materials.